Lab 11 is going to be looking at data from transiting planets across a star, right? So these are exoplanets outside our solar system. If you haven't, pull up the data sheet so you can see how to follow along. Star number 1 has red information in it already. Those are the pieces of information that I've already gone through and done for you. You can also see how to do this with the exoplanet hint document if you would prefer to read instead of watch the video. Okay. You'll notice some of the numbers are missing on your chart. You don't have to do those. Those don't actually have a planet transiting across their sun. If you want to see what that looks like, click on one of the numbers not listed on your chart. To start with, I'm going to click number 1, make my observation. Okay. So I have a summary of the current information that I already know on the left and under here under B. As we go through the lab, these will fill in for you so you don't have to remember everything. If you miss something on the lab, there will be a summary at the end that you can fill the chart in. This is our main piece of data that we're going to start with. It's what we're going to get everything else from. So you can copy and paste it into a Word document and draw some lines on it like I did in the hint document. You can blow it up and look at it that way. Honestly, I find the easiest thing to do is to copy and paste this into a Word document. Use the draw a straight line tool to draw a straight line through your first full period, your last full period that you're going to use. If I do that, I find my first period is at 80 days. My last period here, my last dip, is at 680 days. And I have 1, 2, 3, 4, 5, 6, 7, 8 periods that I'm taking into account. So I take my 600 days, right? 680 minus 80 is 600. Divide it by my 8 periods, and I get about 75 days. So I'm going to click back. I'm going to unzoom it. And I'm going to put in, I'm going to keep 75 in mind, but I want to show you what happens if you don't quite get the right number, right? This is way off. But if you get something that's not within their acceptable error, you're going to get a message that says, nah, go back and do it again. Okay. So we have 75 days. Now we're going to use those 75 days to figure out how far away that planet is from its star. If you think back to Kepler's third law, the units for our time period has to be in Earth years, and that's what this has done. I took my 75 days, I hit calculate it, and it gives it to me in years. Okay. Now, this is Kepler's third law. It looks slightly different. Right? There's this giant M in the middle of it. And M is the mass of the star in question in solar units, or compared to our sun. Since our sun is the base unit, it is a 1. So in Kepler's third law for our solar system, we don't have to take into account the mass of that star. In order to use Kepler's third law for other solar systems, we do have to take into account the mass of that sun. So we throw in our big M here. We will learn about spectral classes later in the semester, but what we need to get from our spectral class is the solar mass, the solar radius, and the temperature, and we will get all of those just from that one piece of information. If you scroll up, that's going to tell us our spectral class. An F5, it's a main sequence star, kind of in the middle of the hot range. So our F5 is going to give us 1.4 solar masses, so I'm going to put in 1.4. Okay. This says automatic in it, which means it's going to populate that information for me. So our planet is 0.38 astronomical units away from its sun. I do want to point out that underneath our next button on each of these pages will be some extra information that will be helpful when you are filling out the questions on your lab. You can find the answers and expand on the answers by reading the information below each of these parts. I would recommend going through a couple of your stars before you do that, just to get the hang and the flow of how this is supposed to go. Okay. So the next thing we want to know is our planet habitable? Right? Is it within the region of that star where liquid water would be stable? So again, I'm going to click on it to make it bigger so we can see it. I do want to note that this is in logarithmic units. Okay? Not as scary as it sounds. It just means that these hash marks that are bunched together, instead of everything going up by the same exact number from 0 to 100 all the way up, it changes. So in our first section, these first hash marks all go up by 0.001. Once we hit the next big hash mark, they all go up by 0.01. Until we hit the next hash mark, they all go up by 0.1, so 0.12, 0.3, 0.4, 0.5, all the way up to 0.9. And then the next 0.1 would give us a whole number 1. So now all of our hash marks go up by the number 1. Till we get to 10, then they all go up by 10. Similar thing happening on the y-axis. We're looking at the mass of the star divided by the mass of our sun. And for us, we are an F5 star that had a, oh no, I forget, what was it? Because I better go back. Okay, so we had a 1.4 solar masses. So 1.4 solar masses, here's my 0.1s, here's 1, so this is 1, and this is 2, so I'm going to be 1.4, which is around here. Okay. So since I'm around here, in order for the planet to be in this green swath, which is the habitable zone, that planet has to be, if I kind of come down here, more than 1 AU away from that star, okay, which means it is not in the habitable zone because ours was only 0.38. Okay. So again, this program's not going to allow you to click the wrong answer. If I tell them that I really wasn't sure, it's going to tell me to go back and look again. Okay. So our exoplanet was definitely not in the habitable zone. Tells me what a good job I did. Okay. Hit the next button. I'm going to make this small again so we can see it. The next step in calculating our information about our exoplanet is to find the surface temperature of that exoplanet. Okay. So we're going to try and find TP, right, by using the radius of the star, the distance that planet is from the star, and the temperature of the star. Okay, all of these three things go into determining how hot the surface of that planet is. Okay. So bigger stars, more massive stars with bigger radius are going to extend out their temperature, their hot temperature further. So the further away that planet is from the star, the cooler it would then be. Right? So we take our F5 star, it has a solar radius of 1.2. Okay, and a temperature of 6,500. Okay, so it's pretty close to our sun. Click calculate, and that means our planet's surface is about 550 degrees Kelvin. For comparison, Earth is about 300, Mars about 210. Okay, next thing we're going to do is we're going to figure out, all right, how big in radius, how big is this planet? Okay, and we're going to do that by figuring out the drop in light output, right? If you think about the more light that planet blocks, the bigger it is. Okay? The program's already figured out that percentage for us. We're going to use the drop in light output, that star's radius, to give us the how big it is. You're just going to click calculate. Okay? So based on how much light was blocked by this planet, that planet is 9.83 times Earth's radius. So it's a really big planet. Right? This next part, we have two different models of density. And one of the questions you're going to be asked is, what does a more complete model of density look like? And you can find some help by the information below your next button. For each of these, you're going to use your green best fit line for our data points, which are our planets of our solar system. They have two different best fit lines for the two different graphs. Your model number one models the density of planets based on how big they are. Our big planets in radius are gas giants, so they have low density. Our small planets are terrestrial, they have high density. We only have one data point of solar systems, so we're going to make a best fit line of our planet's radius versus their densities. Model 2, instead, we're looking at the density of the planets compared to how far they are away from the sun. We learned earlier that the types of materials differ as you are close to the sun and go away from the sun. So with that idea, we can get an idea of maybe how dense that planet is depending on where it formed. Okay. Neither of these are complete models, okay? When I look at my radius of my planet, right, versus my density, okay, I know my planet's radius was almost 10, right, 9.93. And you can zoom in and make this bigger. I've done this already, so I'm gonna just zoom up, and then I kind of read over. So I go up from my x-axis, hit my best fit line, go over to my y-axis, and I get 990. And I get 171 Earth masses for Model 1. Model 2, same density on the y-axis. Instead, my distance from the sun was less than half, so like 5,500. Okay, and much higher density gives me a much larger mass. You're going to find out why you need a more complete model, or what you would take into account for a more complete model later in your lab. In this one, we're going to find the probability of finding it based on its solar radius, and so the radius of the sun and how far away that planet is. You just click calculate it, and it calculates it for you. And here's your data summary. Okay? Any information you missed is there. It even plots on the habitable zone logarithmic graph where it might be. If you have any questions, please don't hesitate to email or Canvas message me.